Every single time you click buy or just mindlessly refresh your feed, you are actually triggering this massive, completely invisible architectural marvel that operates entirely behind the scenes. Today, we're tearing down the front-end wallpaper to expose the back-end blueprint. Let's get right into it.
So, here's our roadmap for this explainer. We're going to build this system from the ground up. We'll start with the client-server foundation, move into the request-response cycle, look at how APIs act as communication bridges, dive into databases, and finally cap it off with the great debate, monoliths versus microservices.
Okay, let's jump straight into part one, the client-server foundation. This is all about building out our core nodes.
You know, if the front end of a website is just the glossy paint and the nice landscaping, the back end is the hardcore structural engineering. Think about making a purchase on Amazon. The back end is that invisible machinery orchestrating the inventory checks, your authentication, and the ledger updates, all simultaneously. It is quite literally the brain and the memory of the entire operation.
Now, what's really fascinating here is how we deliberately segregate these components for security. You've got your web server accepting the requests, the application server applying the business logic, and the database actually storing the data. By keeping these physically or logically isolated, it ensures that if an attacker compromises that web frontline, they don't just instantly get the keys to your core data repository. It's a brilliant built-in defense mechanism.
Which brings us naturally to Section 2, the request-response cycle. Let's map out this flow of data.
I like to think of this HTTP cycle as a highly structured, continuous conversation. The client opens up a TCP connection, fires off a precisely formatted request, and then the server crunches its logic to return a status and some data. It sounds super simple, right? But this literal heartbeat is happening billions of times a second across the web. It's wild to think about.
And rather than using some chaotic jumble of custom commands, this conversation relies on universal HTTP methods. You use GET when you want to retrieve data, POST to create a brand new resource, PUT to update something that's already there, and DELETE, well, to remove it. It's just an incredibly clean, standardized vocabulary for data manipulation. It essentially keeps the entire web speaking exactly the same language.
In return, servers reply with universally understood status codes. Anything in the 200 series means success, like a 201, which tells you your POST request successfully created a resource. Then, of course, there's the dreaded 400 series for client errors, including the infamous 404 not found. You can think of these codes as immediate machine-readable receipts that tell the client exactly how an operation failed or succeeded. But, handling millions of these requests requires some very strict rules of engagement. So let's jump to Section 3, APIs, our communication bridge. An API, or Application Programming Interface, is essentially a very strict digital contract. Developers define exactly what endpoints and methods are actually allowed. If a client sends a malformed request, the API basically acts like a bouncer at a club, just rejecting it right at the door. It is the secure gateway that absolutely protects all of the server's sensitive internal logic.
When engineering these gateways, developers often turn to REST architecture. Roy Fielding, the guy who actually introduced REST, captured his philosophy perfectly. He said, "Versioning an interface is just a polite way to kill deployed applications." I love that quote. It perfectly highlights the ultimate goal here, building communication bridges that are so robust and so hypermedia-driven that they can evolve over time without breaking the older applications that still rely on them.
So, once that API bouncer finally lets the data in, it needs a permanent home. This takes us to Section 4, databases storing the state.
Enter the database, our persistent information vault. Because this piece of software handles the absolute most critical state of the application, think financial records, user profiles, things you really don't want to lose, it usually runs on heavily fortified, completely isolated servers. They are optimized from the ground up for one main thing: highly secure storage and lightning-fast retrieval.
Now, when setting this up, architects generally have to choose between two main philosophies. On one hand, you have SQL databases like Postgres or MySQL. These are rigid and relational. They enforce very strict schemas, rows, and tables. On the other hand, you have NoSQL databases like MongoDB, which offer a lot more fluid flexibility by storing data in adaptable documents or graphs. It really boils down to a classic engineering trade-off. Do you need the rock-solid consistency of SQL, or do you need the rapid adaptability of NoSQL for changing loads?
And as these applications grow to millions of lines of code, we hit Section 5, monoliths versus microservices.
This is basically city planning at scale.
This right here is the ultimate architectural crossroads. A monolithic architecture intertwines all your components into one massive centralized deployment package. It's generally easier to build at first, but it can be absolutely brutal to scale. Microservices, conversely, shatter the application into small, hyper-focused, independent services. This means you can scale exactly what's under heavy load without touching the rest of the system. But, fair warning, it introduces immense complexity when it comes to deployment and monitoring.
One massive upside, though, is that microservices unlock incredible technological freedom. Because these independent nodes just communicate via standard APIs, you aren't locked into a single tech stack for the whole company. Your auth service might run Python with a MySQL database, while your real-time chat feature uses Node.js and MongoDB. It allows development teams to pick the exact right tool for every specific job.
To orchestrate this kind of sprawling metropolis, modern backends rely heavily on cloud computing. They rent virtual machines via IaaS, host their code instantly with PaaS environments, and outsource massive headaches entirely by using SaaS. I mean, why spend weeks building a custom email microservice from scratch when you can just hit a ready-made SaaS API like Twilio? It totally offloads the plumbing, meaning developers can focus all their energy on their unique business logic. The backend really is a modern engineering marvel. Just from a single click on your end, a request is validated by web servers, routed securely across API bridges, processed by incredibly specialized microservices, and finally locked away safely in a database vault. And all of that happens in a fraction of a millisecond. So the next time you're just casually clicking around the web, take a second to ask yourself, how many invisible servers, API bridges, and database vaults is your data traveling through right at this exact moment? It really puts things into perspective. Thanks so much for tuning into this explainer, and we will catch you next time.